Hi everyone, and to all the attendees for this Zoom webinar. I'm Hui Lin from the AI3 office, which stands for Artificial Intelligence, Analytics, and Informatics Horizontal Technology Program Office at ASTAR. So for today's company sharing session, I will start with giving a quick overview of AI at ASTAR before handing over the presentation to three of our AI researchers in ASTAR, Abhishek, Liu Yong, as well as Jay Santelna, who will be going in depth into some of our AI capabilities at ASTAR. Okay, so just to give an overview of ASTAR. So ASTAR is actually Singapore's lead public sector R&D agency. So at a glance, ASTAR has 4 key areas. Under research, we have our 2 councils, the Biomedical Research Council, BMRC, focusing on biomedical sciences, as well as the Science and Engineering Research Council, SCRC in short, focusing on physical sciences as well as engineering research. We have the ASTAR Enterprise, who helps to drive industry development as well as commercialization by collaborating with our key partners in the private sectors. And in terms of talent development and attraction, we have our ASTAR Graduate Academy, which provides scholarships and fellowships to young, aspiring scientific talent. And lastly, we have our ASTAR Corporate Group, which is located in the headquarters. So on the right, is really a summary of ASTAR's research focus, such as chemicals, materials and energy, engineering, infocoms, so on and so forth. In summary, ASTAR has currently a total of 7 HTPOs. They are horizontal technology program officers, which pull together and integrate multidisciplinary capabilities across our research institutes and programs, serving as a one-stop platform to leverage our R&D capabilities from end to end across the value chain and to address cross-cutting national priorities. So AI3, which stands for Artificial Intelligence, Analytics, and Informatics at the top right-hand corner, really helps to develop and deploy solutions to support Singapore's national AI strategy projects. We also have a few of the other HTPOs. I believe probably after this, Intia can actually help to circulate the slides as well. So in AI3 HTPO, we have a total of 5 core AI and data science capabilities spanning across our research institutes. And these include the following: machine learning, computer vision, speech and language technology, cognitive systems, as well as social analytics. Currently, we have a total of about 500 scientists and engineers with AI relevant experts across ASTAR. Okay, so looking at all the ASTAR research entities again, the 2 key research institutes that has the most AI relevant research are in these 2, the Institute for Infocom Research, I2R, as well as the Institute of High Performance Computing. So these are some of the capabilities that they have residing in the institute, such as machine intellection, oral and visual intelligence, robotics, social and cognitive computing, so on and so forth. And those listed in green are research institutes that have some level of AI research, but nonetheless, our office actually works with all of these research institutes very closely. Okay, so for the next few slides, I'll be diving into some of the AI research performed by ASTAR's researchers in several key areas. And later on, our 3 researchers will also be going in depth into some of this research. So in terms of foundational AI, we have human-centric AI research and knowledge reasoning platform to develop AI that will learn and understand like humans and explain their workings to humans. We have learning with less data that looks into research that achieve the same or comparable accuracy even with a small data set. And ASTAR is also looking at next generation AI chips with new architectures. And we have researchers who are building a knowledge and reasoning platform to help augment our scientific researchers to perform complex tasks. In public sector transformation, we have AI research that are with some of a few examples below. So ASTAR has actually come up with an AI-powered system, which have been rolled out in the state courts for real-time multi-party transcription for oral proceedings. And the system has actually achieved more than 90% accuracy. For traffic control, this is a collaboration with LTA, which uses machine learning to dynamically adapt traffic signals. And in terms of healthcare, a few of our BMRC institutes have also researched into multimodal AI for disease diagnosis. And they really look at medical images to diagnose diseases such as cardiovascular and brain diseases, and also to predict possible cancers such as lung and liver cancers. In AI for manufacturing and engineering, we have research in terms of automated inspection, where AI tools with computer vision techniques have been developed to automatically do inspection for defects. There's also research in optimizing manufacturing processes such as surface finishing. And lastly, we have a combination of machine learning, high performance computing, and lab automation to speed up the development of new materials. So this is actually my last slide. Just wanted to end by putting in some of our contact information. So for any internship or career opportunities that any of you may have in AI relevant areas, you may just email us at ai@hq.astar.edu.sg. And if you wish to maybe submit your resume, you can also come into the ASTAR career portal to take a look at all the career opportunities at the ASTAR Research Institutes. Yeah, thanks. I think now I will maybe hand over the presentation to Abhishek. Abhishek, would you like to share your screen?
Yeah, sure. Thanks. Oh, it says host disabled participant screen sharing.
India, can you help to give rights to Abhishek?
Sure, we are on it. Can you try again now?
Okay, yeah, I got it.
Okay.
Okay, can you see my slides?
Yes.
Okay. So good afternoon, everyone. I'm Abhishek. So from the Manufacturing System Division of the Singapore Institute of Manufacturing Technology, that's SIMTech here. So I'll be sharing briefly today about some of the work we are undertaking in AI, with a particular focus on AI for manufacturing optimization. So if you look at a lot of the modern supply chain and manufacturing systems of today, they really operate in complex and uncertain, extremely uncertain environments. And here are certain key characteristics that we observe. So the first thing is extreme nonlinearity of the relationships between actions and outcomes. There are a massive set of possible actions you can choose from, and finding what is the best among this huge space of possible actions is almost like searching for a needle in a haystack sometimes. And finally, you have data limitations. So although people keep talking about big data nowadays, in manufacturing, data is expensive, and hence there is always a lack of data to precisely characterize the uncertainties that you're dealing with. Okay, so given these characteristics, I just plotted this 2x2 matrix to categorize the different, the different classes of techniques you can think about for solving this kind of problems. And manufacturing systems really occupy the top right quadrant here, because thanks to their massive scale and complexity, they really require AI-driven search techniques to find these optimized solutions, to find these needles in the haystack, as I was talking about, and advanced machine learning models that, even in the presence of limited data, can accurately capture action-outcome relationships. On the other hand, if you look at simpler systems, for example, if I talk about a simple linear system, which happens to be massive scale, there are still existing mathematical techniques of linear programming, the simplex algorithm, and so on, that can allow you to find good solutions efficiently. But on the other hand, when you're dealing with highly nonlinear large-scale systems, you really need to go outside the box. These standard classical methods no longer work. So this is really the top right quadrant is really where SIMTech operates in. And the kind of work we do is shown here. So we start with a physical system. Let's assume that's some manufacturing system. We continuously gather data from the real world. This can be through sensors embedded in machines. And this data is then used to understand your environment. So we do different kinds of analytics techniques on the continuous data accumulated to understand the environment, to quantify the uncertainties as best as possible. Then based on this data that we've generated, we'll build predictive models. So these are predictive machine learning models, which tell you what outcome you can expect for a given action. Okay, so these are sort of forecasting models. They will tell you, okay, if I take an action now, what is the outcome I can expect in a few hours time, or a few days time, or in a few months time, depending on the time horizon over which I'm executing my actions. And then finally, based on these predictions, we are going to try to find prescriptions. So a prescription is basically a recommendation on what the best action should be, given all the data and models that you have. And these prescriptions are then enacted in the real world. So they are enacted on the physical system. The system changes, new data is accumulated, and this cycle keeps going on. And over time, you're able to build more and more data. Your predictive models improve, your prescriptions improve, and so on. Okay, so across this whole chain of affairs, there are three key components that we talked about. You have the descriptive, the predictive, and the prescriptive components. And within each, we focus on various, very fundamental state-of-the-art AI techniques. So that covers things like generative modeling, so generative adversarial networks, representation learning models, then deep neural networks for predictive modeling, Gaussian processes. So this is a special kind of model that that allows you to do very, very principled probabilistic modeling. So it's known for its uncertainty estimates, whereas on the other hand, things like deep neural networks sort of have a bad name because they are not very good at representing their own uncertainties. So this is something that Gaussian processes helps you deal with, uncertainties. And then in the prescriptive model, we work on techniques such as evolutionary computation for optimization, Bayesian optimization techniques, and reinforcement learning. So as you see here, we cover a wide variety of fundamental AI techniques and their applications to real world problems. Okay, so utilizing these techniques, here are a couple of projects that we are really interested in nowadays. So the first is, of course, resilient and robust supply chain networks. So this is something that is really in focus nowadays, given what happened in COVID and more recently what's happening in Europe. So we are looking to build network designs for manufacturing that ensure that even under such adverse situations, you can continue operations to the best possible capacity. So a lot of the AI capabilities we deal with here are to do with building models which respect causality. So in other words, they allow you to study how a disruption in a particular node in a network propagates through space and time. Okay, and then it allows you to predict what will happen into the future, simulate what will happen into the future, and accordingly make optimized decisions. And we also look at learning actionable recourse models. So this is basically models that, given a disruption occurs, allows you to come back to your original or desired states as efficiently as possible. So that's actionable recourse. Okay, and the second set of problems that we are interested in is in very large scale simulation-based manufacturing optimization. So the techniques, again, the AI techniques span things like multi-criteria decision support using Bayesian optimization algorithms. And this has to be extended to very high dimensional decision spaces. As I said, there are massive space of possible actions you can choose from. And the second class of algorithms is this transfer Bayesian optimization algorithms that we call. So the uniqueness of this algorithm is that it really teaches machines, and when I say machines, I mean AI algorithms, transferable skills. So it allows a machine to learn something from one manufacturing system and then adapt and apply that knowledge to an entirely different manufacturing system. So transfer that knowledge. So this is a very emerging class of algorithms that we are working on in SimTech. So that's about it from my side. If there's anyone here who's interested in any of these topics, please feel free to contact us, and we'll be very happy to talk to you more. That's it from me. Thank you.
Thanks, Abhishek. Next, maybe you can pass on the presentation to Liu Yong. Liu Yong, appreciate if you can share your screen, please.
Yeah, okay, thanks. It seems I cannot share the slides. Okay, okay, yeah. Good afternoon. My name is Neo Yong from Institute of High Performance Computing, from Computing and Intelligence Department. So this is a brief overview of our department. We have about 70 researchers, scientists, and engineers working on different areas of AI and computing. For example, physics-based AI, to consider physics together with AI, multimodal AI to combine different data modalities to improve the AI performance, efficient AI to make AI more efficient, data efficient, and energy efficient, and also autonomous AI to build AI automatically. Yeah, and we also have a group looking into the high performance computing. For example, the quantum computing, GPU-based computing, and also decentralized computing, including the blockchain. For example, those privacy-preserving computing techniques. Yeah, so this is some work for us in this multimodal healthcare AI. So we work on different areas using AI to solve healthcare problems, working closely with doctors from SingHealth, from other hospitals. For example, use AI to detect lung disease, use AI to detect heart disease, skin disease, kidney disease, and also the eye disease and the brain disease. Yeah. And so these are some media highlights. 2 years ago, we are working closely with Tan Dong Seng Hospital to develop this chest X-ray AI solution, which can help our doctors to quickly screen through the chest X-ray for potential pneumonia infection for COVID patient. Yeah. And we also developed this chatbot doctor for 3,000 patients in community care facilities. So this chatbot help our doctors to engage with the patients to minimize the transmission risk. We also have another work, use AI to detect brain disease, actually using eye images. So this is a very interesting work because our eye is closely related to our brain. So these are some publications in this area. For example, we have a paper in this New England Journal of Medicine with the impact factor about LAN-T1, which is considered one of the highest impact factor in this area, and also in Nature Medicine, Lancet Digital Health, and also top AI conferences. For example, MICAP, EGCAI, Triple AI, SML, a lot. Yeah. So the team published extensively in this area in AI and also digital health. Yeah. And so this is the focus of the team, using the images from eye to detect disease in different organ. For example, our optic nerve is closely connected to our brain. So by looking into this part, we can figure out what's wrong in the brain. And also, the eye is also related to the heart disease and the kidney disease. So the eye is not just a window to your mind, it's also a window to our health. So the team also develops the AI platforms to help our developers to quickly build a model and publish and deploy the model in different areas. For example, chest X-ray, Parkinson, non-local, and some eye diseases. Yeah. And as we know that we need a lot of data to build the AI models, but in some cases, it's not easy to share data across different countries, different hospitals, because the privacy constraint. So in this case, the team work in this area called federated learning. Basically, we can build an AI model without sharing the raw data. So which will be very helpful to build AI model together with partners from different places. Yeah. The team also look into the blockchain to use the blockchain to help our AI scientists to validate the AI models without sending the data across different countries. So the paper also published in Mensa Digital Health. Yeah, so we have many exciting opportunities and projects in the digital health and AI. If you are keen, feel free to contact us so we can see how to work together. Yeah, thank you. Yeah, thanks. That's my part. Yeah.
Okay, thanks, Liu Yong. Yeah, so next we have Jay Sentenak who will be giving the final presentation. Yeah, Jay, can you help to share your screen, please? Thank you.
Yeah, sure. Okay. So can you all see my screen?
Clearer to me now.
Yes. Okay, good evening all.
No, it's okay. 因为第一次我就是觉得 I didn't know about this team.
I'm working mainly
this campus team is
on AI on different domain. I come from Institute for Infocom Research. In particular, I'm from Machine Intellection Department. We mainly focus on developing various AI applied on many domains. That's our focus. And on that, today I'll just try to brief you guys on some of the interesting solution that we applied for one of our work package in the one Huilin was initially showing on accelerated materials development. Here I'm showing one of the work packages what we achieved in how to accelerate the fault isolation in using AI. So basically, I'll just try covering some of the main aspect of how this for fault detection, how this AI can be adopted, and basically I will be giving some 3 scenarios what we try to address. But this project is there for a couple of years, so we are also still open to explore with some of the interns as it is a research project. We are very keen. You guys, if you are interested, feel free to talk. So on the project, we have done some quite interesting work. One is on how to use because in the manufacturing, we know that the faulty data is reasonably low than the healthy data. So how we can use a machine AI solution to capture the faulty in manufacturing part, as well as we try showing like how this AI can be adopted, say for example, FinFET in semiconductor, which is a recent one, GAFET, which is still in research in upcoming semiconductor, how we can extract the knowledge from FinFET, transfer that extracted knowledge to GAFET. And another thing will be one of the interesting case studies, how to use an online classifier, because the reason is the data keeps coming in any manufacturing site, sample by sample. But most of the machine learning, we always collect the data and start training. So the motivation is how, when the sample by sample comes, how the machine learning can adopt. So these 3 things we try showing you. Some of these 3 have been published in top AI and conferences and journal. So coming to the first one is, say what I was trying to show you guys is on how you use generative model, specifically GAN, because we know that GAN has some potential in generating the samples. So here the idea here is, say this is an example I'm showing in semiconductor data set. This is a open database you can access. There's UCI CCOM. So this has the healthy, means the healthy data is higher, around 1,400 plus, but whereas faulty is around roughly around 100. So the imbalance happens. So the main intention is how well we can capture this failure, okay, rather than only focusing on capturing the overall improvising the accuracy. We always know that any overall accuracy will be better, but when it comes the failure scenario, it is more challenging. We developed a generative models which can capture the distribution and oversample in the latent space, because there are many oversampling techniques available since 90s or 80s only. But we developed this deep learning solution, and we found that it has a more potential in capturing especially the failure samples. And the overall outcome is the average classification accuracy is better than some of the past available baseline methods. This work has been published in CIKM, which has 28% acceptance. Just last year, this work was. And further moving, we applied how in a real scenario like the transfer learning can be adopted, say FinFET. For this we featureized using IV curve, so that we try generating using we have a representative data which we try to simulate using TCAD, and this in joint collaboration with Professor Aaron in NUS. There we try mimicking the scenarios in TCAD and capture the data. So for FinFET, we have the model, so which learns, and after learning, how this learned model can be transferred to the GAFET, which is the latest upcoming technology. Here we observed, which is a notably very significant increasing accuracy at adapting the transfer learning. If you are keen on understanding more of this work, it's published in ACS Applied Nanomaterials. You can go through this work. And another interesting work, what I mentioned is, suppose that labels comes sample by sample. Most of the machine learning, what generally people try to adopt is they collect the data and then they try to train the model. But in a real scenario, this may not be always true. So when the data comes streaming, so how we can use this machine learning solution. So on this, we adapted 2 cases, like how the dislocation defect in case of GAFET and bridge defect. Okay, previous in transfer learning, we used a bridge defect, transferring bridge defect of FinFET to GAFET specifically. Okay, so here we had 2 separate scenario. One is on dislocation defect in GAFET and bridge defect in FinFET. This is the idea here. So we use this and mimicked in the TCAD simulation. This data we obtained in real time data. This is, and this one we try to generate from the industry, semiconductor industry, we mimic in the TCAD. Then we capture the data and pass it to the online learning and try to predict the location of the defect. Here what we have done is the location is based on the each region we split, and each region is considered at each classes. So it's say in this case 9 class, here it is 10 class, 5 here the left between the drain and source, that you try to come up with these things. And with that we found it's significantly way improved, more than 90% accuracy. This got recently published in Knowledge Base System, which is one of the AI journals. And all this work so far, what I've shown is the device level. Moving forward, my team in collaboration with NUS, we are working on circuit level defect as well as atomistic level defect. So this is the current ongoing work with them. And we would like to acknowledge the project which is funded by Accelerated Materials Development for Manufacturing program at ASTAR and AME Programmatic, and this is all my team, which is we are working with jointly with NUS team. Thanks, and if you have any specifically you guys are interested, we are also exploring to see any interns from universities can work with us. If you are interested, feel free to reach us. Thank you.